And this is coming from my notes. Page page 41. So this part is from 41, and you would notice the difference. And if you put it together, you will see the difference. So what's this? This means you will still have a reference, linear acceleration, and then you have minus alpha, which is the angular acceleration, cross the distance between O and I, because O is just the reference acceleration. So maybe we do it like this. They're all moments. They are all vectors. And then what else we have? We have this one is actually plus and minus omega squared cross R O I. Now, does it look familiar? This part here. This is the transition or conversion from angular acceleration, angular velocity to linear. And this part is from my notes, page 41. If it does not look familiar to you, review it. Okay. And then as for the moment part, summation of the moment equals to what? Equals to this. And this part is on my notes, page 47. Of course, the formulation I have on page 47 is only true in that configuration. So I'm just going to copy this configuration here. Equals to m times a g y times x bar minus m times a g x times y bar plus ig times alpha. Of course, this must be angular here. This part is on my notes, page 47. This is what you need to recognize, the difference between rectilinear motion. So these two are the governing equations for force and also for moment in rectilinear motion. And this part is what? This part is when you have this one here, that means rectilinear motion. When you have the other two, that means angular motion. So the second set of the force and moment equilibrium is actually not just for angular, but for general motion. With this part for rectilinear. Now you can see the difference. If you do not have any angular acceleration, you don't have any angular velocity, what happens to this? This would just go back to rectilinear motion because it's general motion. If you don't have rectilinear, this is actually not rectilinear, this is angular motion. I'm sorry. Made a mistake. This is angular motion. The first part is rectilinear motion. And these two terms account for angular motion. Linear motion, angular motion. So once you don't have the angular motion components, you don't have alpha, you don't have omega, you don't have this alpha here, the equation will return to this. All right, now with that, we know this is not a rectilinear motion problem because we have geometry. So we have to consider what will be the acceleration developed from here? Now, because this whole thing is under a spinning. So once you have the spinning at the center of gravity, G here, what kind of accelerations that we're gonna do? Acceleration components it will develop. This, of course, we know that there will be tangential, right? There will be tangential component acting at the center of gravity. There will also be normal component, correct? Right? So the first one of them is this acceleration at the center of gravity, the tangential part, and also the normal component part. Remember to always use the positive direction for tangential component as well as for normal component. Now, from here, that means our force equilibrium will have to be developed based on these two. And how do we determine the tangential component as well as the normal component? How do we calculate this? In fact, I already showed the result from the force equilibrium, right? So here, the tangential component is simply alpha. If your distance is perpendicular to the direction of angular acceleration, then you don't have to use cross product because cross product takes the perpendicular operation between two vectors. Now here, the distance is this way, and the direction of alpha is out of the plane. So these two, of course, are already perpendicular. That's why we will just multiply alpha to the distance, which is r from whatever the center of gravity to whatever the point you want to consider. And remember, this has to be from the center of rotation. So this is from G to O, or OG. From the center of gravity to the center of rotation, point O here. What about the normal component? Normal component is omega squared times what? Times R OG. Right? Right? But remember, this is the direction for the normal component, and that's the direction for the tangential component. So from here, we can actually calculate these two first. We already know the angular acceleration alpha, and that's just 5. Now, what's the distance from the center of gravity to the center of rotation? Because that's what alpha is about. What is this distance? Two waiting. Okay, so does anyone know what's the distance from point O to point G? Oh, actually, I made a mistake. People, and the 300 is from the center. I'm sorry. 300 is from the center. Of course, how can you solve the problem? So what's this one here? The distance from the point O to point G is basically the summation of these two, correct? So that is these two. And of course, we will not use millimeter, we'll use meters. And the first one is just be 0.3 plus 0.015, right? And this will give you, actually, another mistake. This is not 15, it's 75. I read it too fast. Okay, so please correct it. This is 75 millimeters. So here, this should be 0.75. And the result is 1.875 meters per square second.